Okay, so today is the third day. I will not, make any introduction. Just a couple of requests. One is still try to stay in with those unless you have a very pressing listening.
Mm-hmm.
Means so that is one thing, and I would encourage the students to interact more, asking more questions. Almost all the questions are coming mostly from the front bench. So there should be more questions from the students, and also try to utilize the T session to engage with the lecturer, because this is primarily aimed at to. And when you ask the question, just hold a little bit patience, indicate to her so that you get the microphone, because your questions are very important to bring more let's say intermediate clarifications to the various topics. And if you have any question, please feel free to ask. There's nothing called a good questions or bad questions, right? Any questions which come to your mind, you want an answer of that, and please feel free to ask that particular question, right? So it is very brief introduction. Today, very interesting topic, quantum Hall effect in graphene, which actually gets the Nobel Prize in graphene. So therefore, so this is the third Nobel Prize in quantum Hall effect in a way. Because it's a 2D system. It's of course graphene, but it's also
proving that it's
proving that it's a perfect two-dimensional material. So therefore, enjoy the talk, okay? So
okay, so before I'm getting to graphene and this lecture today actually is going to be an introduction for my last two lectures, tomorrow and the day after, which in which I'm going to describe developments of the recent years, the recent decades, and that includes my own research. So then the last two lectures will be PowerPoint presentation already, but the purpose of this lecture today is to set the foundations. Okay, so let me first summarize what we discussed in the previous two lectures. We discussed the integer and the fractional quantum Hall effect, and we saw that it's basically you can think of it as one phenomena where the main observation is that first of all you have a quantized Hall conductance. Okay, so quite generally, I'm just reviewing mu. It's some rational. Generally, it's some rational number that you can write as a ratio between two integers, and we discussed the fundamental fractions, which are given by filling factors that are 1 over an odd integer. Okay, and we saw that these are the so-called Laughlin fractions, and these are the in a way the simplest fractional quantum Hall effect liquids. But m equal 1 is also a fraction. Okay, so the integer Hall effect is in fact just a special case of the phenomena, with the main difference being that you can understand it without invoking electron-electron interactions. So already it has the single particle spectrum, which is Landau levels, already gives you the foundations to which you can get the effect without invoking interactions. Okay, so one observation is that sigma xy is quantized. Another is that the longitudinal resistance is 0. Okay, so and these two properties go together because the fact that you have 0 resistance comes from the fact that there is no backscattering, and having no backscattering has to do with chirality of the motion of the electrons. So that's basically the main phenomenology. And one of the things that we've seen in yesterday's lecture, I discussed the topic of edge states. So if you're thinking of the ideal version of a two-dimensional electron gas, which has boundaries, we noticed that the quantum Hall fluid is a state of matter where the bulk is in fact completely inert. It doesn't participate in transport. You can think of, so there are of course electrons in the bulk, but they don't contribute to transport. They are localized. So the transport is on the edge. You have a system where most of it is insulator, in a sense, okay? And in the integer case, it's even a band insulator, so to speak, because there's a hard gap to excitations to the next Landau levels. But the edges are conducting, and because of the edges are conducting with via chiral channels, it's a perfect conduction. So it's a weird situation. It's a kind of an insulator, which has a insulating bulk, but perfectly conducting surface states, okay? And that was the first observation of such phenomena in realistic material. And if you want to, a more generalized concept that it introduced to the field of condensed matter is the idea of a topological state of matter. So the quantum Hall fluid is an example for a topological state. What do I mean by a topological? So this index, this magic numbers that give the quantized Hall conductance are related to topological indices, in the sense that the electron wave function has, in the case of the quantum Hall effect, it has a kind of a winding number that is really characterized by an index, a topological index, which means that it's very robust to details. So the value of the sigma xy at the plateau is independent of whatever complications we introduce in the sample. Even if you add disorder and you add temperature and you add a lot of factors that and you have generalized geometry, the basic feature of the plateaus and the values of the plateau doesn't change. It's very robust. Okay, so yeah.
Yeah, I was wondering that all the discussion that we had till now was primarily for free electron gas. There you wouldn't expect any resistance anyway. I was just wondering that if you had like a problem in which there were whatever periodic potentials and so on, and there were centers with which the electrons could potentially exchange momentum, would that still lead to like this zero resistance, and how to see it?
No, so that's what I tried to explain yesterday. Is we saw that if you introduce a disorder potential, as long as it's not too strong, okay, all it does is to modify the. So in the perfect system, we had something like that we had left movers and right movers that are on separate edges,
right.
And because of that they are ballistic, right? And what we saw is that if I introduce a disorder potential, all that happens is that the pattern of the current flow becomes it goes through the bulk, but still it follows a chiral channel. Okay,
Right.
so in a disordered sample, I'm just reminding what we saw. So if you have, I will not, yeah. So suppose I have a lot of some random potential periodic. It doesn't matter. It can be completely random. And the typical current flow, or the shape of the wave function, if you like,
Yeah.
will look something like that. Okay, and but still, so you're going to have edge states going through the bulk in a sense, because they follow the equipotential contours of some disorder potential. But as long as the potential is not too large, it's still ballistic. Okay, it's still chiral. Okay, so in order to have finite resistance, you need something to. I mean, I'm drawing it a bit exaggerated. Okay, but you need some probability for backscattering.
Right.
Okay.
So in the end, you need like some. So the effective theory that you wrote down for these edge modes, the fact that they are giving rho xx is equal to 0 is just because they are chiral in nature.
Exactly.
So
Exactly.
now, if you could break this chirality in some way, that's the only way
right.
in which you are going to get non-zero.
That's exactly right. And in fact, if you imagine tuning up the disorder potential so that, for example, this constriction that I plotted here becomes narrower and narrower, there will be a critical point where you'll see a quantum phase transition from a perfect conductor to a perfect insulator. And that actually you see it in the lab, that if you're applying a strong magnetic field on a realistic system, there is always some either critical field or critical disorder beyond which there is a transition from zero resistance to infinite resistance. It's really like a superconductor to insulator transition. Okay, it's really even an analog of that, I would say. Okay, so yeah, right. So beyond, so up to some critical value, this phenomena is robust to disorder, and it follows from the chirality. Exactly right. And this is an example. This is a special example of something more general that we call a topological protection. Okay, so in the particular example of quantum Hall, the topological index is this number nu, which is the coefficient of the Hall conductivity, and it's related to a more general concept called the Chern number in band structure, and therefore and that's and as long as it's non-zero, it provides the topological protection. Okay.
Though I don't see this clearly, I take this here as a statement that this is chirality which is protecting, giving rho xx is equal to 0. The theory that you started with was like free chiral theory at the boundary.
Right.
You also gave an example of this, interacting chiral theory, which was this Lettinger liquid thing, which is still chiral and hence gives you rho xx is equal to 0.
That's
okay.
Right.
Now, is it reasonable to think that all sort of quantum Hall systems that you get, in which you get rho xx equal to 0, they should all be described by some chiral theory living on the boundary?
Yeah, that's
so
right.
If I can discover
that's right.
2D chiral theories, that's the space of quantum Hall.
Exactly. That's exactly right.
I think.
That's exactly right. And
are there known other examples apart from free and the Lettinger liquid which are known to be chiral, like interacting theories which are chiral?
Probably they are, but
there must be, of course.
But if you're looking for something that is described like the simplest field theory, so this is actually what I did yesterday, is to show you that the theory for the edge states for fractional and integer are actually related by the same. If you look at collective variables, that describes the low energy physics, and it's basically qualitatively the same. Okay, it's just a ballistic transport of some density waves. Okay, and its chirality is what gives it the ballistic feature. Okay. Now, to get such a state, in fact, all the family of quantum Hall states are like that, what we call quantum Hall fluids. You need a magnetic field, okay? And you need a magnetic field to get also any finite Hall conductance, right? So you're breaking time reversal symmetry. And about 2 decades or so, or even before, I don't know, that theoretical physicists started asking themselves whether there is a generalization for this phenomena to cases where time reversal symmetry is not broken. So maybe we can get similar things without a magnetic field. And indeed, some theoretical models were proposed that later on were also realized in experiments to some more generalized concept called a topological insulator. Okay, and the quantum Hall effect turns out to be just a special example for that, in which requires the breaking of time reversal symmetry. But there are models where you can get very similar phenomenology, but without the breaking of quantum Hall, of time reversal. And how do you manage that? You do need something that will give a non-trivial topology of sorts, that will have a topological index that can take different values that are different from 0. And it turns out that a few simple models were proposed where you're considering just 3 electrons on a lattice. Okay, this is a 3 electron model, although of course you can also generalize it for interacting systems. But the important ingredient was to have a spin orbit coupling. Okay, so this class of topological insulators that I'm talking about invoked another degree of freedom, which is the spin. Up till now, I didn't discuss the spin, right? I mean, I showed you how to get quantized Hall conductance for 3 electrons, for the hydrodynamic field theory for the fractional, but in all of that, there was only orbital motion, no spin. And in fact, you can ask yourself, okay, but the electrons have spin half. So what does it do? In the standard quantum Hall effect, it doesn't do much, right? It just, okay, so you have 2 separate spin up and spin down states. And in a magnetic field, you also have some coupling to the spin, just because of the Zeeman effect. But that's a separate thing. If you imagine the Zeeman effect would be very small, you would just double the number of chiral channels. That's all. Okay, so it doesn't play a significant role. Actually, it does play an interesting role in interacting system, and I'll discuss it tomorrow. But for the purpose of the concept of the quantum Hall effect, it will just increase or multiply the number of plateaus by 2, okay, because of the spin, the discrete degree of freedom, okay. However, when you have spin orbit coupling, you can get an interesting situation where if you add a term that couples the momentum to the spin, you can get a topological index without breaking time reversal symmetry, right? Because if I'm writing a term in my Hamiltonian that looks like this, for example, k is it's a momentum and speed, sigma is a vector of Pauli matrices. Such a thing is invariant under time reversal, okay? But it does have, it can have, okay, you can have models where this term will have a well-defined sign, which is either +1 and -1, and we call it helicity. This is something that also exists in high energy, right, and defines the neutrino, and the helicity can be + or -1. And that introduces a topological index of a different kind that is not an integer, is not a part of a sequence of infinitely many integers, but it's just + or -1. Okay? So this is called a Z2 topological index. And if you relate it to some physics model that invokes spin-orbit coupling, you can actually relate it to this concept of helicity, where helicity is the direction of the spin multiplied by the direction of the momentum, okay? So now, there were several simple models that were proposed in the literature that actually started this whole field of topological insulators. One is by Kane and Melet. It's a very famous paper. I think it's 2005, or I don't remember exactly, but if you Google it, you will obviously get, and that's one. And another one, I'm not writing the models, I'm just mentioning the names. Another famous model that seems to be relevant to some physical systems is by Bernevig, Hughes, and Zhang, Suchang Zhang. So it's abbreviated as BHZ model. So these are examples for very simple models for Hamiltonian that you write in K-space, and they have some term that in both models there is a term that exists because of spin-orbit coupling of some sort, and there are different kinds of one. And what these models were able to predict is that you are going to get a state of matter, and this is, by the way, I forgot to mention that this is in 2 dimensions, okay? It's in 2 dimensions. You can also introduce topological insulators in 3 dimensions, but the 2-dimensional version is really very, very similar to the quantum Hall effect, okay? And the nature of the state is just like what we had in the quantum Hall effect. The bulk, you have a bulk insulator, that's why it's called a topological insulator. The bulk is insulating, but there are edge states that are topologically protected. However, if you have time reversal symmetry, they cannot be chiral, okay? So they're not chiral, but they're going to have another topological index that protects them, and that's the helicity, okay? So, so once again, it's a state with a insulating bulk and perfect conducting surface. And the same thing happens also in the 3-dimensional case. You can have the three-dimensional bulk that is insulating, but the surface state that now are going to be two-dimensional are going to be perfect conducting, okay? Okay, so so now let me tell you what is the phenomenology of this state. Let me tell you what comes out. I don't want to spend time on writing the models. You can find them in the literature, and they're actually very simple because they start from a solid state, tight binding model that is familiar to anybody who studied the elementary solid state, but it's a tight binding with some special terms, some hopping terms that are related to the spin degree of freedom in such a way that you can solve the spectrum, and you see that you get a spectrum where you have bulk states with a gap, just like Landau levels. However, they're no longer going to be flat bands, they're going to be something more complicated, but they are always edge states that are topologically protected, and if you introduce disorder or whatever, the system is still robust and maintains its structure. So if I just look at the idealistic model, yeah, yeah.
Mention the Haldane model as well as the other model, I think.
Okay.
In between, yeah.
Very good. So
SSH model.
SSH. Okay. The SSH actually, SSH is a bit problematic because it's in 1D. There the concept of edges is I mean it's kind of a too simplified, I would say, version of it, but you are right that actually Haldane was the first to write a model that doesn't have chirality and that nevertheless is a topological insulator, but in his model there was breaking of time reversal because it includes a flux, so it's something that has negative and positive fluxes, so it doesn't belong to the class that doesn't break time reversal symmetry. Okay, that's the difference, but yeah, it has a very similar phenomenology, and so it was written by Haldane as just an exercise for an afternoon exercise for a student with no physical justification, but turned out to be a very, very important. Okay. Was not even the reason why Haldane got a Nobel Prize, but yeah, thanks for mentioning it, for the credit. Okay, so let me just summarize the phenomenology that you see. What comes out of the model, okay, is that if I have my 2D sample, and by the way, this is true for both the BHZ and the Kahneman-Leh. They both, they're different models, but they give you the same structure. You have a bulk that is insulating, and the edge states, there are edge states that carry the transport, and these edge states are not chiral, but they can be thought of as two copies of the quantum Hall effect with opposite chirality and opposite spin, okay? So that altogether time reversal symmetry is not broken, but the helicity index is different for the two states. So what do I mean by that? So there is one, so let's, for example, think of the simplest version of such a term that you can write down is that you have a kz times sigma z, okay? So spin is polarized in the z direction, it has up and down, and then you get on one edge, you get that the spin up states have a positive chirality on one edge, and on the opposite edge you have okay, this is one spin, and so this is let me just write it down. This is for S equals plus half, and for S equals minus half, you get left moving. Okay, this is the spin, and the other arrow is the momentum. So here you have Sz equals minus half. Okay. Okay, and the other edge has an opposite chirality. Okay, so in fact you can simply think of it as two copies of the quantum Hall effect. Each of them is quantized. The momentum is quantized, or the chirality is in one direction, but one of them has also a spin plus and the other has a spin down. So the momentum and the spin are locked to each other in such a way that you can see that the upper edge that I plotted has helicity. So the upper edge has helicity plus 1, and this edge has minus 1. Okay. So for the same spin, so both the blue and the red have the same helicity, although they have an opposite chirality. Okay. So basically, this is what comes out of the theoretical models, and the question is, what do you measure in the lab to see it? Because now what will be the whole conductance of this thing? If you just measure, just like we discussed in the previous two lectures, you measure voltage and current and two terminal, 4 terminal, whatever. What will be the sigma xy? Of course, it will be 0, right? Because time reversal symmetry is preserved, right? So sigma xy is going to be 0, okay? Nevertheless, you can do a very simple transport measurement that will observe this topological protection, and that is measuring a 2-terminal conductance. Okay, so maybe here I have to backtrack a little bit and tell you that even for the standard for the quantum Hall effect, you can also get the plateaus of sigma xy by not measuring sigma xy, but rather just the 2-terminal conductance. Okay, so let me explain that first, and then you'll see that the generalization to the topological insulator is trivial. So what do you measure? This is my sample, and I have only two contacts. This is called a 2-terminal measurement. Okay. In a 2-terminal measurement, you you only have two contacts, so both the current and the voltage are connected to the same thing, and in fact it doesn't matter if you apply voltage or so let's assume that you are I put here an ampere meter. Okay, this goes to you close the circuit some way, and this is the current, and I also connect a voltage to the same contacts. Okay, and let me call this V. Okay, and now I define a two-terminal conductance G to be simply I over V. Okay, so let's first ask ourselves what will we measure in the integer quantum Hall effect. Okay, the integer quantum Hall effect, you had you basically let me go down a little bit. You have one chiral state going this way, and another one. Let me actually draw it in the same color. This is right mover. This is left mover. And the current I, what I called I, is just IR minus IL, right? It's just the difference between the two. And in order for them to be different, you need to put a finite voltage. But what is the voltage? The voltage is a difference in chemical potentials between the two contacts. So let me call it, I can denote the voltage here by VL, and this is VR, okay? And V is just VR minus VL, okay? Now what will be the conductance? Okay, so and maybe just to be able to explain it a little better, let's assume that the contacts cover the whole sample, so that electrons can be injected from one contact to from this contact to the right, and from this contact to the left. Okay, and remember, we assume that the simplified version, the bulk is insulating. So in order to create current, you need to send electrons from the left to the right or from the right to the left, but they are chiral edges, and one of them is closer to one side and the other is closer to the other side. So in fact, what is going to be this potential difference V, which is the difference between right and left, is actually the voltage difference between this point and this point. Okay? Okay? Because that's where the electrons are injected. Okay? They come from a contact which dictates some chemical potential, and that determines the local voltage. And V is, so you see the voltage difference cannot be interpreted as Vx and Vy as in the pictures we drew yesterday, because it's actually the difference between these two corners, okay? Now, therefore, if I'm insisting on separating it into x and y, respecting my Cartesian coordinates, let me call this part of the voltage I call Vx, and this part I call Vy, okay? And now if I'm looking at my original definitions of what was Rxx and Rxy, so rho xy is Vy.
Efrat?
Yeah?
So this could be the other two corners as well also, right?
Yes, but the thing is that in the other corners, of course, that's a very important subtlety. So the contact, this is just a metal contact. The chemical potential is uniform over the contact.
Okay.
But the electrons on this corner are not being able to connect to the chiral channel, right? So so if you imagine it as you're putting a bias and the electrons start to flow. The electrons flow from this corner to the left and from this corner to the right. Okay? So actually they don't equilibrate with the chemical potential on the other side. Okay? Okay? That's an important point. Otherwise, of course, everything will be zero. Okay?
Yes, okay.
Okay, so we're talking about a non-equilibrium situation. Okay?
Okay.
So therefore, so I can write here rho xx and rho xy are related to either Vy or Vx divided by the same current, right? But what I have in the conductance is neither this nor the other. It's actually the denominator in the expression of G. So let me write it like this. The denominator is Vx plus Vy, right? Because it's the voltage difference between this and this corner. So it's Vx plus Vy, okay? And this is actually what it is. And if you are now rewriting it in terms of rho xx and rho xy, you see that it's actually the current cancels and you get 1 over rho xx plus rho xy. Here I'm being a little sloppy because, actually I'm not being sloppy with the units, sorry. But yeah, this is basically what it is, okay? Conductance is the two-terminal conductance is not 1 over rho xx, it's not 1 over rho xy, it's 1 over the sum, okay? And because if rho xx is 0, because this channel is ballistic, so there's no voltage, Vx is actually 0. So this actually is nothing but 1 over rho xy, which in the ideal case is equal to sigma xy. Okay? So for one chiral channel, it's going to give me just 1 times E square over H. Okay? So, and now we are back to, so let me just write it down. So G for the chiral case is going to be just 1 factor of E square over H. It's quantized conductance, which is in fact equivalent to sigma xy. Now I'm coming back to my helical system. Now what I have is I have two copies of the chiral case. Each of them has different spin, and because of that, the helicity is protected, because to backscatter, you need to flip the spin, okay? So it's in fact not allowed. It's not allowed in the topological insulator. So you have two ballistic channels. One has the right mover on the upper edge, and the other has the right mover on the lower edge. But when you account for the two terminal conductance, they don't cancel each other, they add up, okay? And the reason is that, okay, maybe I'll, let me plot the, okay, I'll quickly plot it again. So you have, this is spin up, okay, and this will be my other spin state, which is right moving. And now I have my contacts, and now the thing is that if I denote the voltage here by V left and this is VR, now if I'm looking at the blue channel, it's the left moving electrons are injected from the top corner on the right, and this guy is VL, okay? So in fact, the contribution to the conductance is the same as the opposite chirality, okay? So they add up, and what you're going to get is just 2 times E squared over H. That's the overall contribution, and it's going to be a plateau, okay? If you are changing a parameter, it will be quantized at that value, although you apply a gate voltage or change some setting, some experimental parameter, and that behavior is named a quantum spin Hall effect, okay? Okay, it's basically just 2 copies of the quantum Hall effect for separate spins, and therefore what is chiral is the particular spin, okay? So that's why it's called the spin Hall effect, okay? But to measure it in electric transport, if you don't have a probe that is sensitive to the spin, you can also measure spin maybe, but that's more difficult. But in just electric transport, it appears as a quantized conductance that is doubled, okay? Now, so this all was based on some theory, yeah?
Yeah, so just curious to know, so in this case, so all those incompressibility and other arguments, do they hold also?
Yes, they hold, but they hold in the sense that you're going to have, I mean, the models that I mentioned are really single particle models. There's no interactions, and they give you electronic states that are localized in the bulk with a hard gap. Okay, so they're like they're band insulators, but they have gapless edge states, which have this helicity. They're called helical edge states. Okay.
Okay.
Okay. And again, the topological protection is a bit more subtle than what we have in the quantum Hall effect, because it's not chirality, it's the fact that to backscatter you need to flip the spin. Okay, so, and that is a forbidden process. There are two sectors that are separate. Okay,
Ma'am?
Yeah.
Ma'am, like in this model, though we neglect the interaction between electron and electron, but there would be a higher interaction compared to what we had in
So in fact, first of all, here the interactions may not even be very strong, because unlike in the Landau levels, the band is not flat. So interactions may be, you can find situations where the interactions are negligible, but if interactions are there, okay, that still, you still have that. They still give you a topological insulator, and they may even give you a fractional topological insulator. Just like in the quantum Hall effect, something very similar can happen. Okay, that you can have analogs of the Landau levels, which are some kind of flat bands with well-defined helicity, but of course in the case where you have time reversal symmetry breaking, they always come in pairs that are positive and negative, but you can have also fractional states, okay, in principle. And you can have all sorts of other things, but if you're just thinking of adding interactions as a perturbation, they will not modify the nature of this. They will still maintain it. Yes.
So maybe I missed something because I came late. Why did we not mention spin when we talked about that Dirac Hamiltonian model with the integer quantum Hall effect, maybe in the first or the second lecture?
Yeah. So I just said that I ignored the spin in my lecture before, and the only reason is that its role in the case of the quantum Hall effect, in the usual case, is trivial. It just adds another channel, and because of the magnetic field, you can have a Zeeman splitting. But its role is trivial. It just adds another channel for each spin flavor, okay? But here, the spin is locked to the momentum, and that gives you a different kind of topological index, okay? Yes?
So in this formalism, this ballistic transport is important, right?
Yes, right. But it is actually a consequence of having a topological protection.
Right.
Okay.
So I was just wondering that, this ballistic transport comes from your spin momentum locking.
Yes,
in this
exactly.
Right. So, if I could imagine, let's say, if there is no spin momentum locking, but you make a device, for example, right, where your mean free path is much larger than the device, the dimension of the device.
Okay, but
do you get this?
It's like having a clean, just like, but that's not protected. Then as soon as you have a boundary or some defect, it spoils it, right? The whole point about the topological protection is that you can you are welcome to introduce impurities, and again, unless they are very, very disordered, it's going to, the effect is robust, okay?
So what I'm saying is, actually, I understand that there will not be topological protection, but if I can fabricate my device, for example, with very low disorder, let's say the ballistic design, right? So do I get this? Can I expect that we get this kind of quantized Hall?
That's a good question. The answer is yes. So in fact, there were, experiments in the early 80s when they started fabricating narrow wires, like quantum wires, they're called. You see quantized conductance, yes? Yes, that's true, yeah. Right. But then they have to be small and, mesoscopic, basically. But the quantum Hall effect and the quantum spin Hall effect, you can see it on a macroscopic sample of, millimeter size, okay? Okay, so
can I ask one practical question?
Yeah.
So in our experiments on this 2DEG, this gallium arsenide, aluminum gallium arsenide heterostructures. So often we work with mobility, let's say 10 to the power 5 centimeters square per volt second, some of that order. I mean, typical quantum Hall effect experiments are done on one order of magnitude higher mobility.
Yeah.
But in that, these kind of devices, we often come out we have these plateaus, right? But we also sometimes we see some very strange behavior. So I could show you some data maybe tomorrow.
Right. So
any idea on this?
So yeah. So first of all, I mean, integer or quantum Hall effect you typically see even in dirty samples, like the original von Klitzing experiment was done on very dirty silicon MOSFET, but the thing is, in between integers you have many fractions, and if you have and the fractional states, because they are driven by interactions, they may compete with other kinds of electronic many-body states, some of which are insulating, right? So, for example, the filling factor 1/7 or 1/9, you will not see. It will not be a quantum Hall, although you can write down a Laughlin wave function and everything is fine, except that it doesn't have as good an energy as a Wigner crystal, which is an insulator, right? So now, whether in one sample you will see this fraction or the other, or which one will be bigger, depends on details, okay? But the potential of having a quantum Hall fluid exists for any filling fraction that is one of these series, okay?
Previously you mentioned this sigma xy will be 0 for this helical.
Yeah, so sigma xy is 0 in this case, but so sigma xy is 0, but the two-terminal conductance is going to be
in two-terminal conductance, we are separating the spin up and spin down state.
Yes, because right, but when you measure electric transport, both spin flavors will give you, if you apply voltage in some direction, the current always flows, the net current always flows in the direction of the voltage, right? Okay, so the two channels, they contribute, they add up when you account for the electrical resistance. If you look for the spin, if you define a spin Hall effect, it will be like the analog of the sigma xy, okay? Okay, if you could do a spin resolved measurement, you could also see it in a Hall effect, but it's a Hall effect of the spin current and not of the electric current. Okay? Maybe you need to think about it a little bit to convince yourself. Okay, let me go on. Now, I mentioned all this. I promised to talk about graphene, and I still didn't get to it. But this was one motivation for me to discuss this time reversal symmetric topological insulator is that it turns out that in graphene, in a magnetic field where you do break time reversal symmetry and you have Landau levels and all that, we'll discuss it soon. One unique features of electrons in graphene compared to the standard two-dimensional electron gas is that you can have a realization of the quantum spin Hall effect, and there the sigma xy equals 0 doesn't come from lack of magnetic field, but it comes from charge neutrality. Okay, so another way to get sigma xy equals 0, if you have a magnetic field but no charge, you have a symmetry of electrons and holes, then sigma xy will once again be 0. But nevertheless, you can have a state that is topological, okay? And that is unique to graphene. So just to mention about topological insulators, there are material realizations that that account for the BHZ model at least. So there are quantum wells of mercury telluride and cadmium telluride heterostructures. They're very powerful, but well, very, very hard to work with. I mean, I wouldn't even try, but there were experiments done on them by Molenkamp that appear to see this quantized conductance, but it's very hard. It's a bit, the results are a bit controversial, okay? It doesn't look as nice as the quantum Hall effect, okay? But in graphene, actually, you can see a version of this physics because of other reasons, okay? So now I'm coming to graphene, and and what is special about graphene, about what we call a standard two-dimensional electron gas is in fact something that has parabolic bend, okay? So the dispersion of energy to momentum is k square, okay? That's the standard kinetic energy of free electrons or any band structure that has a parabolic or approximate parabolic shape, okay? What is special about graphene, and of course it's not the only example, is the low energy dispersion of natural graphene is Dirac, is basically Dirac spectrum, namely the dispersion is linear in K and not quadratic. And that changes the nature of the Landau levels. So that's what I'm going to introduce. So let me first give a bit of introduction. What is actually graphene? It's yeah.
No, understand.
Okay, fine. Let me plot. So first of all, graphene is just a single layer. I hope everybody knows that. I'm sure everybody knows. That in 2010, Gaim and Novoselov received the Nobel Prize for isolating a single layer of graphite, okay? And you can also get a few layer graphene, bilayer, trilayer, and so on, but a single layer, this is what I'm going to talk about today, is just one atomic layer. So it is truly two-dimensional, okay? Unlike the 2D electron gas that I discussed before that you get in semiconductor heterostructure, it's not that you confine electrons to an effective single channel. It's basically really atomically thin single layer of a crystal, and the crystal structure is a honeycomb. So let me plot it the best I can. It's a honeycomb of it's all carbon atoms, okay? So on the corners of these hexagons you have carbon atoms, but notice that this is one of the first examples you give in undergraduate solid state course for a lattice that is not a Bravais lattice, okay? So why is it not a Bravais lattice? Because there are two sublattice sites that are not equivalent to each other. So if you look at all these sites, okay, which I call, let us call these A, okay, they're A sublattices. They form a triangular lattice, which is a Bravais lattice, but there is an inequivalent set of sites that will denote by B, and A and B are not equivalent. So the unit cell is the unit cell of a triangular lattice, and inside the unit cell you have two sites, okay? So if you want to write a tight binding model and represent it in K-space in a quasi-momentum state, write down a Hamiltonian for such thing, you have to write it as a matrix, as a 2x2 matrix in the sublattice, okay? I hope these concepts are familiar to everyone. And what you find, and then you can, many years ago, the band structure of graphene was studied. It's actually a very simple exercise. In the simplest tight binding model, you can imagine that there is hopping between nearest neighbors, so it's always between A to B and vice versa. And what you find is that you get if the graphene is in its natural state, namely it's not doped, it's not, there's no gate voltage that adds carriers. In its natural way, the spectrum looks like this. First, let me write the Brillouin zone. The Brillouin zone of triangular lattice is hexagonal. Okay, so this is I'm plotting the Brillouin zone in K space. Sorry. Okay, this is kx, ky, and you see that there are actually two special points that the corners of the Brillouin zone, one is called K and the other, let's denote with a slightly different color, is K prime, okay? There are two inequivalent points in the Brillouin zone that are not related by reciprocal lattice vector because, of course, there is here, this corner and this corner are the same, right? They are related by reciprocal lattice. So there are two special points in K-space that are inequivalent. We call them valleys, okay? It's the notation. And if I zoom in on one of the valleys and plot the energy spectrum, so let me try to plot it schematically. This is energy as a function of kx and ky, where kx and ky here in this figure, they are measured away from the point k, okay? So you sit on k and go away from it. How does the energy spectrum look like? It's a Dirac cone, okay? So it looks like this, and it has circular symmetry. And if I want to write an expression for it, and of course it is an approximation. If you go to high energy, the band eventually curve. But when you look at actually, for pretty much a wide range of energy, it looks really linear dispersion. So epsilon is approximately given by it's just proportional to k. Okay, that's how the spectrum looks. Let me just briefly remind how you get it, how you get this dispersion, because in order to see how you get an energy dispersion, you need to diagonalize the Hamiltonian, and when you do it in a tight binding, you can convert it to an effective Hamiltonian in K space, HK. So for each K, but because it has a sublattice structure, you get, actually, let me write it, sorry. What's going on? Okay, so let me write it like this. So you get an effective Schrödinger equation in K space, where this psi you can write as a spinor in the AB sublattice, okay? And phi A and phi B are some functions of x and y of the two-dimensional plane, and the Hamiltonian is a 2x2 matrix in this sublattice basis. Okay, so now I'm writing how it looks. Sorry, there is, I forgot a prefactor. There is a prefactor H bar VF times, it's an off-diagonal matrix that you can write like this. Okay, and what I wrote here, let me just write it a little more nicely. Okay, it's a 2x2 matrix. What I'm writing now is just this is just for valley K. For the other valley, you get a time reversed version of this, okay? So I'm not writing it explicitly, but actually the full Hamiltonian is actually a 4x4 matrix, one for valley K, one for valley K prime, and each of them is a 2x2 matrix, okay? That's the formalism. Now, when I present it like this, notice that the valley degree of freedom serves like another spin half, right? So the way to think about it is that we really have another discrete degree of freedom that is spin-like this valley. It has two states, okay? And each of them have a decoupled, they're decoupled from each other, and in the low energy sector, there's almost no transition between them because it's a high momentum transfer, okay? Now, there's a compact way of writing this, sorry, it's the wrong, the compact way of writing what I just had here is don't catch me on minus sign. I'm not sure everything is exact, but I can more compactly write it as K dot sigma, where this sigma, be careful, is not the spin, it's the sublattice pseudo-spin degree of freedom, okay? So this is not spin, this is for each spin. In addition to this, you have a spin index, the usual spin, but this is just a way of representing it in a compact way, okay? Now, how do I get how do I diagonalize it? So, yeah,
Question.
right?
The fact that this is off partial, is it just because is it just because like this is supposed to represent like jumping from a sublattice?
Exactly,
there's
exactly.
no A to A thing.
Exactly.
Nearest neighbor.
That's right. The nearest neighbor, you're completely right. Nearest neighbor gives you just jumping from A to B or B to A. If you add next nearest neighbor, you can get corrections, but they don't change because they are weaker and so on. They don't change the structure so much, and yeah. So basically, this is what you get, and that's really a Dirac, right? It's really a Dirac. I mean, when you convert it to real space, it gives you a Dirac equation. Now, interestingly, an easy way of getting the spectrum is, I mean, you can, it's easy to diagonalize a 2x2 matrix, but one way of getting it quickly is to notice that if you take this matrix and you square it, you can get the spectrum of you get the spectrum of a standard quadratic Hamiltonian. So if you can solve the following Schrödinger equation, and that will give you the square of the energy, okay? And this HK will be now a diagonal matrix, and this will result epsilon k, which are almost what I wrote here, but notice that this is a solution for the square of the energy. So in fact, there are two solutions, negative and positive, right? And that's the Dirac cone. So the solution is that you have plus or minus h bar VF k absolute value, okay? And therefore you have a Dirac cone, and therefore, depending on where your Fermi energy lies, you can either have holes or electrons, but in pristine graphene, when it's not doped and not connected to gate voltage, the natural state, the energy lies exactly at the Dirac point, okay? So it's a charge neutral point. So natural undoped graphene, the Fermi energy is really here. Zero energy, okay? So, yeah, sorry, no. Okay? So, so you can have if you're tuning your Fermi level, I mean, you don't have to tune it. The natural state, as I said, the energy is zero. Okay, so that's graphene, and the next question is, what happens in a magnetic field? So what I wanted to achieve today is to show you how the Landau levels look in graphene, just like in the free electron gas of the Schrödinger type that we solved. How do we introduce a magnetic field perpendicular to the system? We introduce a vector potential which shifts the momentum, and we get harmonic oscillator states, and all that will be now very simple, except that the momentum appears in the Hamiltonian linearly and not quadratically, okay? So the way to deal with it, so now let me write down, I have a non-zero perpendicular magnetic field. I now can prove that I can rewrite my Hamiltonian in terms of harmonic oscillator operators. So this is something I didn't discuss it in the previous lectures, but if we go back to the electron gas of the parabolic type, one way of compactly introducing the effective Hamiltonian that we get is that we can introduce ladder operators, which are just the usual harmonic oscillator ladder operators, and they are defined as follows. So there's the magnetic length over square root 2, dy plus x minus x, sorry, let me see if this is the gauge that I wanted. No, so sorry, that's not what, that's y, not y, okay. There's a factor that settles the units, 1 over LB squared times y minus yk, okay, where yk is exactly the same guiding center coordinates that we discussed yesterday. So this is a definition of A dagger is the conjugate, so it's not a Hermitian operator, right? If you take the same Hamiltonian, harmonic oscillator Hamiltonian that we wrote 2 days ago, you can easily show that it can be expressed in a very compact way in this form, okay? This is just another way of writing the harmonic oscillator potential using the ladder operators. And what I wrote here is not for graphene. This is for parabolic, band, okay? Okay, this is, I'm just retracing. Okay, now comes graphene. Graphene in a magnetic field, for exactly the same reason, you have a vector potential. So if I'm going back to how the Hamiltonian will look in a magnetic field, instead of, it will still be a 2x2 matrix in the sublattice index, but instead of these momenta, I'm going to get linear expressions with A and A dagger. So for Dirac electrons, this is what you get. It's sorry, let me just be a little careful with the units. Here there is some prefactor that has dimensions of energy, okay? It has the magnetic length here, and then 0, A dagger 0, okay? This is how it looks like. And when I square it to get the spectrum square, just like what I did for zero magnetic field, what I'm going to get, it's very easy, I think, to recover, that you're going to get an A dagger A, but with no factor half, okay? There's no factor half that you have in the usual harmonic oscillator. And therefore, just to cut a long story short, let me plot how the Landau level spectrum. So once again, you're going to get Landau levels, okay, a quantized spectrum, but the energy spectrum is not equidistant. That's one feature of it. It's going to be, so let me write it down. The Landau levels are going to be plus or minus this prefactor times a square root of.
So this missing factor half is consequence of some symmetry, right?
Sorry?
This missing factor half.
Yes,
that's
exactly right. Yeah, that's right. Because, so notice now there's really an interesting feature here. This index n, this quantum number, is integer which includes 0. Okay? It includes 0. And the plus minus is just the sign of n. Okay? So for each n, for each non-zero integer, you have two solutions, +1 and -1, +2, -2.
So they say this is some consequence of the index theorem itself, right?
It's it's actually just it's a consequence of, yeah, okay, you can relate it to
RTR's type of thing.
That's right.
Type of thing is.
But it really comes, if you trace it back to the lattice structure, it goes back to, there's a parity symmetry.
Yes.
There's a parity symmetry. And right, so in fact, this is how the Landau level spectrum look like. Notice first of all that it's not, it goes like a square root of n. So the Landau levels are not equidistant. They are getting denser and denser. But the first gap, first of all, okay, so there are two important features that I want to stress. Let me just plot the Landau levels. There is to use a straight line, and again, now I'm assuming an ideal system, no edges, okay, and all that will come to later. There is a Landau level at 0, okay, and that's very special. There's not such thing in a parabolic band. And the next Landau level is, let's say, somewhere here. Right, and they're all degenerate as a function. So when I plot these lines, it's actually, there is once again a guiding center, or a k, the quantum number, there's a quantum number k, just like what we had in previous lectures, the guiding center coordinate that is related to the momentum in the x direction, let's say. But the Landau levels are degenerate just in the same way as in the usual case. But the structure of the levels is that you have a particle hole symmetric structure with this is n equal 1, this is n equal -1, and then the next Landau level is going to be something like this, okay? So the sequence, so this is n equal 2 and n equal -2 and so on, and then 3 and -3. So they're getting squeezed, but there are two things that I want to stress. The first thing is this Landau level, okay? There's no analog in the standard parabolic band, because what's special about it is that it's exactly, you have a vastly degenerate band exactly at zero energy, okay? And if the Fermi level happens to lie inside it, it's going to be half filled and it's particle hole symmetric, okay? Now, there can be things that can lift the degeneracy, we'll talk about it in a minute, but yeah, there is a Landau level 0, and it's particle hole symmetric, it's a charge neutral. The other Landau levels are similar to what you have in parabolic bands in their phenomenology, but they are particles or holes, right? Yeah.
Particle hole symmetric at equal to 0, but it's a non-Majorana.
No, it's not a Majorana. No. Yeah. Right. Exactly. Right. It's simple. They're simple Dirac electrons. That's right. But it's when I plot these energy levels as a function of k, they are flat. They're degenerate as a function of guiding center. But in addition to that, there are additional degeneracies, because let's count for each k, each momentum k, how many states there are, okay? And we have to now recall that there actually, okay, let me backtrack. There was another thing that I wanted to stress before I get to the discrete degrees of freedom, and that is the fact that the energy scale, which describes the gap that we have for between the 0 and the 1 Landau level, is much larger than the h bar omega c of the standard 2 deg, okay? And it's actually larger by typically a factor of 100 or something like that. Why is it so huge? Because look at what is the energy scale. It's basically dictated by the ratio of the Fermi velocity to the magnetic length. So it's larger than the typical parabolic band by factor of LB to the lattice constant. So the lattice constant is angstroms. A typical magnetic field for 10 Tesla is 100 angstrom, okay? So typically this is a huge energy scale, a huge gap. What it means is that at much higher temperature, you can already observe the quantum Hall effect, okay?
And more resistant to so.
In the sense of getting you can see the quantized plateaus at much more modest conditions. You don't have even, you can go to sub-Tesla magnetic fields and temperatures of above 10 Kelvin or more, or even room temperature in principle, you can see it, okay?
Why is it?
Well, in practice, okay, realistic systems are dirty and so on, but if you have a strong magnetic field, you can even see it close to room temperature, okay?
So it's n equals 0 persists if the degeneracy breaks for the paper?
Okay, so good. So now let me talk about the degeneracies. Okay, so all what I wrote here, this 2x2 Hamiltonian that I'm writing, and the spectrum, everything is calculated for a single spin and a single valley, right? There is also the other valley, and the other valley has a very similar Hamiltonian, just A and A dagger are interchanged, okay? So it has the same spectrum, it has the same structure, they're symmetric to each other. So we have two copies of the same Hamiltonian for the two valleys, and in addition, and the two valleys are degenerate, okay? So there is already valley degeneracy, but there's also, if there is sort of a spin degeneracy, which of course is not exactly a degeneracy because there's always a Zeeman coupling to the spin. We are in a magnetic field, but the Zeeman coupling in graphene, the G factor is very small. So in comparison with this huge energy gap, the Zeeman energy is negligible. So the spin is almost degenerate, okay? So at least in this limit, each K state in a Landau level has 4 degeneracies, 4 flavors, okay? So we have K up, K prime up, K down, K prime down, and we can think of them as 4 flavors, okay, in principle. So the manifold of spin states is not SU2, it's SU4, okay? And of course, this is just an approximation because I neglected the Zeeman.
I don't know, do they see Fermions here?
I'll get to Fermions tomorrow.
Okay.
Okay? I'm just explaining the basics and yeah, right. Yeah, the short answer is yes. Okay, but I want to stress the fact that in terms of what kind of, if we are now thinking of what happens if I'm introducing interactions, okay, I'm now talking about the non-interacting tight binding result in a magnetic field, but we have here flat bands. Interactions we know are important and they can create all sorts of things, including fractional quantum Hall state, but not only that, they can also generate other kind of correlated states that break the symmetry of the spin or valley or any of the flavors. And in comparison to the usual electron gas that has only 2 spin states, it's much richer because the manifold of different flavors is bigger, okay? So in principle, we can have ferromagnets, we can have valley ferromagnet, valley anti-ferromagnet, we can have spin valley entangled, we'll have all sorts of, we can have all sorts of broken symmetry states that come from interactions, and they don't even have anything to do with the quantum Hall effect, okay? Just because of Coulomb interactions, okay? And all that story is what I'm going to tell you in the last 2 lectures, but here I want to stress the basic ingredients, that there are several differences compared to the standard 2DEG. First of all, just the energy scales are such that it's much easier to see the quantum Hall effect compared to silicon MOSFET or to gallium arsenide. And second, there's a 0 Landau level, okay? And you are going to see some quantum Hall states that are special to the 0 Landau level, and they will have quantized sigma xy, but it's quantized at 0, right? Because it's particle Hall symmetric. Nevertheless, I call it a quantum Hall effect, a quantum Hall state, because it has certain features that are similar to the quantum Hall states, but in many ways it's still different because of that feature, okay, that it's particle Hall symmetric.
But and it persists even after electron interaction.
It actually comes from electron, and we will discuss it tomorrow. But the third important difference compared to the previous, the standard quantum Hall is that you have 4 flavors, and these 4 flavors are for monolayer graphene. If you're considering bilayer graphene or tetralayer, then you have even more. And then there is a richness of phases that you can have, and okay, and we'll discuss all that later. Now, so the last thing I want to say about this is that I said that for each case state in the simplified picture, we have a degeneracy of 4, okay, spin and valley. But now various things can split the spin and valley. One of them we already mentioned, the Zeeman effect. So what happens if I don't neglect the Zeeman effect? Then actually, so this zero Landau level actually splits into, it splits into 2, okay, let's say spin up and spin down, okay, and the splitting between them is, okay, it's the, let's call it EZ for Zeeman. Okay, so there is some splitting between the spin states, but an important thing to notice, although it doesn't look so good in my figure, sorry. Okay, let me maybe draw it a little more nicely. So the splitting to the spin up, this is a plus, oh sorry. SZ plus half and SZ minus half. The splitting is symmetric, okay? So whenever there is really an inherent particle Hall symmetry in the problem. So whenever you split the 0 Landau level, there's always particle and Hall symmetric state. In this case, it's the spin. Now, in principle, also the valley degree of freedom can be split in an analogous way if you apply some electric bias that favors one valley over the other and breaks the inversion symmetry, because the 2 valleys, the K and K prime, are related by inversion. It's a bit difficult to see it in monolayer graphene, but in bilayer graphene or higher few layer graphene, it's actually quite easy to split the valley, okay? And I'll discuss it tomorrow as well. But there's another thing that splits the valley, or can naturally splits the valley. What splits the valley degeneracy is anything that breaks inversion, okay? Now, in the bulk of the graphene crystal, it has an inversion symmetry. The crystal has this property, and that's actually what dictates all these nice properties of the spectrum. But if I have a finite strip, on the boundary, I break the reflection symmetry, right? So the A and B sublattice are going to be non-symmetric on the two edges. What is the effect on the spectrum? And that actually reminds very much of what happens in finite size quantum Hall systems of a standard electron gas. The boundary conditions change the energy. Now, if I'm looking at the higher Landau levels, okay, so let me now plot on the same graph what happens near the edge. Suppose I plot this as a function of the guiding center, and somewhere here I have the edges, okay? So let's call this Ly. So I have a finite size strip, and on the strip I'm breaking the valley symmetry, okay? So the valleys, the K and K prime, are splitting in some way. What will happen in the higher Landau levels is that near the boundary you always rise the energy if you are electron doped, or if they're Hall doped, it's particle Hall symmetric. So what you're going to find is that these higher Landau levels split in some way, and they always go up on either side, okay, either edge, but there is a splitting. There is some splitting. The details depend on the boundary condition, whether it's a zigzag or armchair and so on, because the lattice structure is a honeycomb, remember? So it has at least two kinds of clean edges, okay? But interestingly, and then there is a complete particle Hall symmetry. Okay, so this is how the Hall-like levels will look like. But what happens to n equals 0 at the edge?
So
yeah.
Why do you get that small bump?
Which
when you make this two?
Actually, it's not always looking like that, and now, as I said, it depends on the details. Okay.
Okay.
Of what kind of boundary conditions you get. If you have the difference is so. This is something I didn't want to get into, but because it's really relevant only for very clean crystal.
No, so this drawing you are doing on the basis of a continuum model, or on the?
Yeah, actually, so there is a very nice paper by Herb Fertig and Louis Bray.
Louis Bray, yeah.
From 2006. Okay,
yeah,
actually, let me write down. Fertig
and Bray, yeah.
And Bray.
Oh.
This is actually one of the first papers on the quantum Hall effect in graphene that were just analyzed the non-interacting model, but they did a detailed calculation of how the edge states look in the two types of, so there are two types of boundaries for honeycomb crystal, because you can either cut it here, this is called the zigzag, right? Or you can cut it on this edge. The boundary condition is very different because the wave function is a superposition of A and B. It satisfies a more subtle boundary condition here, whereas here you just make one of the sublattice 0.
Yeah.
Right, but in both cases, so in each case you get a slightly different picture, and that you see very nicely in this paper of Bray and Fertig and Bray, okay? But if you look at the 0 Landau level, It doesn't matter if you choose the armchair, the zigzag, or even something in between. You always get particle-hole symmetric splitting. Okay. So this is how the edge states, the edge states spectrum look like. And now, what is the significance of that? So now, if you want to analyze the quantum Hall effect on this in this graphene system, so let me replot the Landau level, and now remember that in the bulk we had 4 states. Let's now forget about the spin splitting. Okay, let's neglect the Zeeman energy. So each of these K states is fourfold degenerate, but on the boundary you split the valley. So each of the branches has 2 flavors, only 2, just the spin. Okay. So if now I put my Fermi level, let's say here, okay, what is going to be the contribution to the Hall conductance? So again, you'll have a quantized Hall conductance, but if the Fermi energy is in the electron-like side, then you're going to have right movers here, left movers here, okay? And the quantized Hall conductance, you just have to count how many channels you have. It's going to be 2 times E square over H, okay? Why 2? Because of the spin degeneracy, okay? And similarly, if your Fermi energy is somewhere here, you're going to get -2 times E square over H. And if you go to the next Landau level and it's completely full, it's going always to jump by 4, okay? Because you have 4 flavors for each Landau level. So altogether, the integer quantum Hall effect, which is, again, this is what won the Nobel Prize, because this was really a proof that the monolayer graphene is 2-dimensional, was a measurement of the quantum Hall effect. And again, it's once you have the system, the measurement is easy. It's relatively high temperature and modest magnetic field. So let me plot schematically what you get. This is as a function of the electron density or Fermi energy, where 0 is when you are exactly at the Dirac point, and there you get nothing. In this simplified picture, you get sigma xy equals 0, okay? But in fact, if the Fermi level is just slightly above 0, you get, now I'm plotting sigma xy, so this is sigma xy. It looks like that. So you have one plateau here, symmetric, and then you have a jump, and this is the next plateau, and so on and so forth. Of course, in the experiment, I'll show you the data tomorrow, but it doesn't look as smooth, but you see very clear steps. Interestingly, so the formula for the sigma xy, which accounts for all these degeneracies, is 4 times E square over H times N plus a half. That's the formula. Okay? So, and let me, so the half is for the case that N equals 0. Okay? Actually, let me see, yeah.
So,
right. So in fact, you have plus or minus that,
So
right?
just wondering, if your Fermi level is bang in the center, then wouldn't you have some scattering between these two because they're so close?
No, they're not close. What do you mean? So first, if your Fermi, if this is the spectrum, if your Fermi
at the edge,
yeah,
at the edges.
Yeah.
So at the edges, if it's right at the center, then that node is so close that I would anticipate some scattering.
What this figure, actually, this plot is for, this is as a function of guiding center, okay? And this is plus Ly over 2, just like in the usual. So if you have a strip of finite width Ly, Ly is macroscopic, okay? As long as it's many magnetic lengths apart, they don't scatter to each other. It's exactly the same thing, okay? So you once again have a right mover in the left.
Close. But aren't the energies so close? Because it's kind of branching off from the center point.
No, the energy.
So it's slightly.
This is the energy. So
he's talking about the scattering between the particle and whole branch, right? He's not talking about between the two chirality, but not on the two.
Between the two
particle and whole branch. Right. That is, I think, protected by symmetry or something.
No, but okay. That's so. If you ideally, if you are at 0 temperature, then you are either at plus A Fermi, or if you're asking what happens if the Fermi energy is exactly at 0. So in practice, what you're going, so you see what's going on. This is actually exactly this point, right? This is this point.
Yeah.
Now, in practice, what you see is, again, okay, that's what you see in a relatively modest magnetic field, and as long as the non-interacting picture is applied, okay? However, okay, this is just a teaser for what I'm going to talk about tomorrow. In sufficiently strong magnetic field, you start to develop a plateau here at 0.
Can you draw that?
I can draw it, but I will get to it tomorrow and explain where it's coming from. And that's now going to be a new type of quantum Hall state that is very different from the others. So what I plotted here, these plateau states are just the regular integer quantum Hall effect. And that's what you get from a non-interacting picture when you assume a finite strip and so on. And everything looks similar to the standard quantum Hall effect, except the degeneracies here are dictating the step size, and the fact that at the near the 0 doping, you get sigma xy that is either plus 2 or minus 2, okay? Yeah.
For bilayer or trilayer systems, is the gap between the plateaus is still the same, or it's different?
Oh, okay, good question. So actually, so there again, if you are in some limit where you don't have a splitting of the flavor, the other flavor degrees of freedom, the step size will be bigger and it will be reflecting the degeneracy, okay? So that's the simplified picture that assumes that basically there is always full degeneracy of all these flavors, except on the edges. And the edges always split the valley because they break inversion symmetry, okay? But in real experiments, what people have seen is that you start to develop in between plateaus, and they're not coming from fractional quantum Hall effect, although you also have that. You have 1/3, you have also certain fractions that are similar in nature to what you can find in parabolic 2D. But in addition, you get quantum Hall states that are of a different kind of many-body. Okay? Yeah, so basically this is, I think, this is where I can stop for today. It just sets the stage for what I'll tell you tomorrow. Yeah?
One practical question. So this calculation that you have shown, this is based on this two-probe measurement.
Which calculations of the... For the conductance?
Quantum spin Hall conductance that I have shown.
Yeah, right. Yeah. Okay, but this was for this was for the topological insulator.
Yes. Yeah.
I still owe you. Okay, so I told you that there's going to be a sort of realization of that in graphene, but I still didn't explain why.
Right. So,
and whether that's correct. Okay.
Okay. So my question is, when we measure, we usually use 4-probe measurement. You
can use 4-probe, and you can but if you have a 2-terminal experiment, that's one of the easiest way, let's say, of verifying that you have a quantum spin Hall effect. Okay.
So question is I assume the result would be still the same, but you were stressing on 2-probe measurement, so that's why I just a little bit confused.
Yeah, because if you do the 4-probe measurement to get sigma xy, it will give you. I can tell you the answer without measuring. It will give you 0.
Hello.
Right?
Oh, sorry.
Right. So there's no Hall conductance or Hall resistance, because it's time reversal symmetric. There's no magnetic field here. Okay? But nevertheless, there is some, so the good topological index here that distinguishes the upper one edge from the other is helicity and not chirality. Okay? So just in electric transport alone, you cannot see a Hall effect. If you could measure a spin resolved transport, if you could do that, you could measure it, yeah. And then it would be just 2 copies of the same. But if you just measure electric conductance, a 2-terminal conductance is equivalent to measuring the ballistic. So it's basically measuring how many ballistic transport you have in either direction. Okay, that's actually what it measures. Yeah.
I just missed the point that you made the last slide.
Yeah. Okay.
Which you talking about?
Yeah.
There, the sigma xy is 2 Easter.
Yes. Yeah.
And those are given by those 2 plateaus.
That's right. Yeah. Right. Yeah. Exactly. Sorry. So no, there's nothing at the center. And again, this is just the first quantum Hall experiment. This is what you see. You showed. You see.
This is
okay.
at the edge.
Yeah, and you can interpret it in this edge set picture, but this is what I'm plotting is more or less what you see in the experiment. Yeah, it's exactly. So you have a contribution. If n is slightly bigger than 0, then you get right. There's a sharp. So there's right at n equals 0. There is a transition from -½ to or -2 to +2, and it's a sharp. It's like the transition between plateaus in the quantum Hall effect. Okay, but there's no plateau at 0. However, that changes if you have strong enough magnetic field. You always start to develop a plateau, and that's where the interesting physics comes from. Okay. Yeah. Okay.